Welcome to section 1.2 applications of propositional logic. Again, we are using the text Discrete Mathematics and Its Applications by Kenneth H. Rosen. The class is Math 160, Discrete Methods, here at Anderson University, South Carolina. This is Dr. Gilbert Eyabi. Objectives. We shall be interested in the following subheadings: translating English to propositional logic, system specifications, Boolean searching, logic puzzles, and logic circuits. We would end right here and not treat the optional subsection. So number one, translating English sentences. How do we translate from the Queen's language English to propositional logic? Steps to convert an English sentence to a statement in propositional logic would be: number one, identify atomic propositions and represent these using propositional variables. What are the individual propositions? Identify all of these. And secondly, you want to determine appropriate logical connectives so you can build the compound proposition. For example, if I go to Harris or to the country, I will not go shopping. What are the atomic propositions here? Go to Harris, go to the country, and go shopping. You do not have to worry about the word not, because that is simply wiggle whatever the statement is. And observe the presence of comma. That means the first two atomic propositions are together. If I go to Harris or if I go to the country, so that will be parentheses, then I will not go shopping. That is if, then. So if P is I go to Harris and Q is I go to the country, R is I go shopping, then we can translate from English to propositional logic as follows. P or Q, all of that in parentheses, implies not R. If I go to Harris or I go to the country, parentheses, then I will not go shopping. Beautiful. Another example, you can access the internet from campus only if you are a computer science major or you are not a freshman. This example could have surfaced in the days when internet just came around and accessing the internet on campus was such a wonderful privilege. But we are not interested in that. We're interested in converting this English sentence into propositional logic. So what are the atomic propositions we have here? Number one, access the internet. Number two, computer science major. Number three, freshman. But observe here that we have the word or the phrase only if. If you recall, when we introduced P implies Q is the same as P only if Q. So life is good. Okay. Now, with some other words, for example, the word when, which we're going to see later on, if you have P when Q, it's usually interpreted in the reverse. Okay, Q comes first before P. So watch out when dealing with things like those. But for only if, P only if Q is exactly the same as P implies Q. So life is good. So what comes before only if? Access the internet. So if A is access the internet, then that will be A implies. What comes after only if? You are a computer science major or you are not a freshman. Again, that is together because they all appear after only if. So we have C or not F. So you can have access from campus if you are a computer science major or you are not a freshman. That was easy. Now let's move on to more conversion or translation from English to propositional logic. But this one is mostly used by system and software engineers. And at times it's very specific to that discipline, but it is still translating from English to propositional logic. Example, the automated reply cannot be sent when the file system is full. See that word I just mentioned? When. Go back and look at the various ways by which we can write P implies Q. If I use the word when, then P implies Q is actually seen as Q when P. So Q comes first when P, and that means P implies Q. And putting that in perspective, we can translate this software and engineer specification as follows. And putting that in perspective, we can translate this system and software engineer specification language as follows. The automated reply cannot be sent So if we let P denote the automated reply can be sent and Q denote the file system is full, then in translating this statement, remember when would be this first one implies the next. And that would be the file system is full. So if the file system is full, then not whatever comes before when. And since what comes before when is the automated reply can be sent, it's going to be not P. So Q implies not P. If the file system is full, then the automated reply cannot be sent. Okay, so in your mind, you are moving from when to if then. And if it is if then, it's P implies Q. If it is when, it switches. So you are turning it back to the form P implies Q. Now, it doesn't matter that much whether it's P or Q. All those are just dummy variables. So what you have to remember is the statement before when and the statement after when. If I were to switch it in the form P implies Q, it goes the other way around. Okay? And that's beautiful. Now, what does it mean when we say a system is consistent? Consistent system specifications. A list of propositions is consistent if it is possible to assign truth values to the proposition variables so that each proposition is true. One more time. A list of propositions is said to be consistent if it is possible to assign truth values to the proposition variables in all the propositions so that each proposition is true. Well, let's give you an example to demystify this concept. First proposition, the diagnostic message is stored in the buffer or it is retransmitted. The diagnostic message is not stored in the buffer. If the diagnostic message is stored in the buffer, then it is retransmitted. So what I do first is I translate each of these from English or from system software engineer language to propositional logic and ask myself, can I find truth values that will cause all the propositions to be true? If that is the case, then we say it is consistent. Otherwise, it is not consistent. So let P denote the diagnostic message is stored in the buffer, and let Q denote the diagnostic message is retransmitted. Then we have the following translation. Number one, the diagnostic message is stored in the buffer or it is retransmitted. That will be P or Q. Next, the diagnostic message is not stored in the buffer. That will be not P. And lastly, if the diagnostic message is stored in the buffer, then it is retransmitted. That will be P implies Q. Is it possible to find truth values for P or Q that will cause all three propositions to be true? Well, what happens when P is false? Let's look at it. If P is false and Q is true, then P or Q would be true or false, which is true. Not P would be not false, which is true. P implies Q would be false, implies true, which is true. So I have found truth values such that all three propositions end up with the value T end up being true. So we say the system is consistent. So when P is false and Q is true, all three statements are true, so the specification is consistent. Now, if I add a fourth proposition that says the diagnostic message is not retransmitted, then I'll realize that there is no way I can come up with a combination of either P being false, Q being true, or Q being true, or Q being false, P being true, such that all four propositions are true. Therefore, if a fourth message, the diagnostic message is not retransmitted, is added, then the system specification is not consistent. Again, for it to be consistent, I should be able to find truth values which will be assigned to the proposition. Again, for the system to be consistent, I should be able to assign truth values to the proposition variables so that each proposition is true. It's like they are simultaneously true if I assign those particular truth values to the proposition variables. You will get many more examples in class and from your textbook. Even more exciting are logic puzzles. you should be able to solve logic puzzles just using the ideas we have mentioned before. First of all, you have to translate from English to propositional logic and then see if you end up with something that makes sense or not. Let's try this example. An island has two kinds of inhabitants, knights who always tell the truth and knaves who always lie. You go to the island and meet two people, A and B. A says B is a knight. B says the two of us are of opposite types. What are the types of A and B? Of course, without translating to logic, if you think about it rigorously, you should still be able to come up with the correct answer. But logic makes it even more fun. So let P and Q be statements that A is a knight and B is a knight. So P would be A is a knight and Q would be B is a knight. And of course, that means not P would be A is a knave and not Q would be B is a knave. Now let's enjoy the work. If A is a knight, then that means P is true. Remember, P is A is a knight. That means P is true. Since all knights, of course, tell the truth, what does A say? A says B is a knight. So Q must also be true. And of course, if B is a knight, then B is telling the truth. So B says the two of us are of opposite types. Oh, that's a problem. So if A is a knight, then B has to be a knight. But if B is a knight, B says the two of us are of opposite type, that means both A and B cannot be knights. And the solution starts falling apart from the original initial statement that A was a knight, and so we can go the reverse direction. Again, so if A is a knight and P is true, since knights tell the truth, Q must also be true, then we would have P and not Q, or not P and Q would have to be true, but it is not. So A is not a knight, and if A is not a knight, that means A would have to be a knave. In other words, not P must be true. But if A is a knave, that means A lied. Therefore, B is not a knight, and B would have to be a knave. And of course, B says the two of us are of opposite type. That means B lied. So both of them would have to be of the same type. And what is that same type? They're both knaves. Okay, it's beautiful to do it just by thinking or by using logical operatives and logical variables and propositional statements and propositional logic. But it's beautiful to solve some of these problems, and you'll get some more from your textbook and your written homework. The next applications to propositional logic would be logic circuits. And I actually just love these. They are very simple, but really interesting. I'm going to ask you to construct for me some very beautiful compound propositional logic circuits. Or I may give you a logic circuit and ask you to give me the compound proposition that was used to construct it. All you have to remember is that this symbol means the inverter. P goes in, not P comes out. This symbol right here is the OR gate, okay? And this is the AND gate. So P and Q would go in and the output is P or Q. P and Q would go in and the output is P and Q. Just remember the shapes. That's the inverter, that's the OR gate, and that is the AND gate. Okay, whatever way you want to use to remember this two, just remember it. Okay, very important. Now let me show you an example. I need you to build a logical circuit for me, and the logical circuit will be one that will carry the compound proposition P and not Q parentheses or not R. P and not Q parentheses or not R. So look at the atomic propositions we have here. We have P, we have Q, we have R. I'm going to need a not R. So I'm going to pass R through an inverter. I'm going to need a not Q, which means I'm going to pass Q through an inverter. Then whatever output comes from the inverter, I'm going to pass P and not Q through the AND gate. And then whatever comes out of the AND gate and whatever comes out of the inverter for R, I'm going to pass both of these through the OR gate. Complex? Don't think so. Okay, let's see how that goes. So R passes through the inverter, that gives us not R. Q passes through the inverter, that gives us not Q. P and not Q passes through the AND gate to give us P and not Q. Not R moves on smoothly. P and not Q together with not R passes through the OR gate to give us PN, not Q, all of that, or not R. Simple yet beautiful. You should be able to do more complex ones than these, and I'll give you some for your homework, and we shall look at some more of these in class. This brings us to the end of section 1.2, and I look forward to seeing you in section 1.3. Thank you, and God bless you.